before we start working on any of our features like extending the world or programming the camera, it's a good idea to keep track of the game's frames per second, because we want to know that even when we add additional features that our game is still performing close to the desired 60 frames per second. So to do that, we can create a new script within game, and I'm going to call this utils.py. And in this util script, I'm going to write a small function for drawing text to the screen. So first I can import pygame. Then I'm going to define this small function called drawText. And in this function, we're going to pass the screen, the text that we want to write, size, color of the text, and the position of the text. Drawing text in pygame, we need to create a font object. So I'm going to go font equals pg.font.sysfont. And I'm going to pass none here, and that's just going to take the default font on our system and the size of the font here. Next, we're going to create our text surface, so that's the actual text that we want to render. So from font, we can go font.render, text, true for anti-alias, and the color of the text. Next, from this text surface, we can extract the rectangle. So textRect equals the text surface, and use the handy method of getRect. And inside here we can specify the position, so the top left of this rect will be in the position pos. Now that we have our text surface and our text rect, we can simply blit this to the screen, so screen.blit, text surface, text rect, and that should be fine. Going back to the game class, we can first import this function from utils. Then scrolling down to our draw method, it's going to be the final thing that we draw. So after everything else is drawn, we're going to draw our FPS in the top left corner of the screen. So we can go draw text. It's got a few arguments, so I'm just going to split it out like this. So first self.screen, then we want FPS equals, pass it in some curly brackets so we can use format. I'm going to take round because we just want to take an integer. And from our self.clock object, we have a method called getFPS. And that'll provide us with the current frames per second. Next, we're going to put in a size. So I'm just going to make this 25. RGB color, so I'm going to make it white in this case. And the position, so I want top left of the screen, so just 10 pixels in the X, 10 pixels in the Y. Now we can run our game. Okay, and up in the left we can see that we're basically running at 60 frames per second, but that's not much of a surprise because our game is still very small, so that's kind of what we hoped for. The next thing we'll focus on is writing the camera class for our game. We could make the world bigger now, but we have no way of navigating to other parts of the world, so it's probably a good idea if we write in the camera class now, so that when we make the world bigger, we'll be able to actually explore it. So going to the game folder, creating a new script called camera.py. Going to be where our camera class is held, so importing pygame as pg. Going to make the class camera. Then inside the init method, I'm going to pass it the width and the height of the game screen. So the reason for this is I want to make this camera react to the mouse's position rather than the keys. So like if the mouse is in near the top of the screen, then the camera will move. I prefer to have this kind of functionality over keys down for these types of games. So I'm going to hold self.width and self.height here. The next thing we're going to define is the amount the camera has moved in pixels, because we're going to apply the kind of the inverse of this to the rest of the world. So this is the amount the camera, and we're going to call this self.scroll. I'm just going to initialize this as a 2D vec, starting with like 0 pixels. So it's moved 0 pixels in the x and 0 pixels in the y. Now I'm going to define a few variables that are going to help us change the scroll value. So the first is the difference in x. I'm going to initialize that as 0, and difference is y as 0, and also the speed of the camera, and that's going to be 25 pixels. Then we can define our update method. So, like I said before, we want to move this camera based on the mouse's position. So first extracting the mouse's position, we can pg.mouse.get pos. And then we can say if the x position of the mouse is greater than 97% of the screen's width, so it's right on the right hand side, so self.width, applying a small reduction, so 97% of the screen, we're going to say self.dx equals minus self.speed, because we want the world to move in the opposite direction. We can do a similar logic for the x coordinate, but for the left hand side of the screen. So in that case we're going to say if it's smaller than self.width, but applying a massive reduction, so that's if it's in the first 3% of the screen, then we can do self.dx equals self.speed. If neither of these conditions are true, so if the x coordinate of the mouse is in the middle of the screen, then self.dx is none, so we don't want any change in the x. And this is our logic for the x movement. We're going to write a very, very similar thing, but for the y movement. So in fact, I'm just going to copy and paste all of this logic and just change some of the values. So this needs to be 1, because we want to extract the y coordinate of the mouse. And this is going to be height. This is going to be the difference in y. So I'm going to make this height. And similar for these, so that's y and y. And then after we've kind of calculated for each update tick the difference in x's and y's that we want to apply, what we can do is update the camera scroll. So we're going to say self.scroll.x. Because we've already applied the inversion here, we're just going to say add this on, so self.dx, and same thing for the y. Okay, and that's all we need right now for our camera class. So going to the game, as I said, very simple camera class, but it should be enough for what we want it to do. So from.camera, import this camera class, then in it, I'm just going to put in a few comments, world, and here it's going to be anything to do with the camera. So self.camera equals camera, and we're just supplying it self.width and the height, the width and height of the screen. Our camera does need to update as we play the game, so the first thing we're going to put in our update method is our camera, and it updates. No other arguments needed. And from this camera, we'll have this scroll value, which we can apply to anything we render on the screen. So inside So here, where we're rendering the grass tiles, we actually want to extract the camera scroll in the X and the Y. So as our camera moves, as we move with our mouse, then the rest of the world will also move with it. We're also going to need some scroll values here, because this is where we're rendering like the trees and the rocks. Exactly the same thing. Self.camera.scroll.x, and where are we? We want to be here, I think. Self.camera.scroll.y. Okay. Let's have a play. Let's see if this has worked. Okay. Seems to be working. So going to the top of the screen is going to move the world effectively down, to give the illusion that we're moving up in the world, and it seems that all directions are working. Okay, good. Having now written a camera class for navigating the world, we can have a go at increasing the size of the world, which can be done by going back to game. Then we have these simple arguments inside of our world class for defining the grid size. So if we increase these to 1550, so that's 2,500 tiles in total, and running the game again, we get this, which if we go down, you can see that clearly there's a problem, because whilst our trees and rocks seem to be rendered hopefully in the correct positions, our grass tiles are basically not rendering beyond the edges of the screen. So if we return to our world class, it's fairly obvious to see why this has happened, because originally when we were writing our code, we defined this grass tile surface, and we defined it to have the same dimensions as our screen, so the width and the height of our screen, because at the time that's all we needed. However, now, because we want to render images that are outside of the screen, basically has run out of surface to render to. So nothing beyond our screen is getting rendered. So to remedy this, we need to change these size values, the width and the height, to be the same size as this world that we want to create. So we're going to have to calculate the dimensions of the world. For the x dimension of the world, we can first take the grid length. We can then multiply it by the tile size, but we also need to multiply this quantity by 2. Because if you remember when we looked at the isometric polygons, that if our tile size is 64, then the polygon will have a height of 64, but its width will be double that value, so 128. So that's why we also need to apply this scalar of 2 here. We can do a similar thing for the y, but for the same reasons, we don't have to apply 2, we can just apply this, because the height of the isometric polygon will be the tile size. But we are drawing blocks, so I'm just going to add on a little bit more to the y dimension. I mean, it doesn't really matter, but just to make sure that we capture the bottom blocks. So, and this is going to be 2 times tile size. The other correction that we need to do is to correct these offsets, because these offsets were valid for when we had a 10 by 10 that was rendered in the middle of the screen. This is no longer relevant, so I'm going to get rid of this, but we will need an X offset. So the reason for this is half of our tiles will basically have negative X values because of the transformation. And this surface will only take in positive values. So we've basically got to shift all of the isometric polygons so that all of them have 0 or greater values. So to do this, we can apply another offset. This case it's going to be half of the width of the grass tiles. So do self.grasstiles.get width divided by 2. Before we run the game again, we need to go back to the game script. We need to apply the same offset values here. So getting rid of self.height over 4, because it's no longer valid, and getting rid of self.width over 2, but replacing it with the same offset, so that's self.world.grasstiles, extracting the width, and dividing by 2. So now if we run the game again, okay, so our screen has started off slightly offset, but more importantly, all of our grass tiles and our trees and rocks seem to be rendered nicely. So good, we have now extended the world. Can also do a bit of a stress test for our game and really increase the world size to see if we get any drops in our frame rate. So if I double these values to 100, and then now we have 10,000 tiles being drawn to the screen, running the game, and we can see that it's taking a little bit longer to load up. Then just scrolling around and looking at the FPS value, we can see that it's not dreadfully slow, but our FPS rate has taken a little bit of a hit, and we're kind of always between like 40 and 55, so maybe on average we're losing about 10 or more FPS. So one way to fix this, or one way to optimize our code further, and this is a very simple way, but I found that it's actually pretty important, is whenever we define an image or a surface, it's always important to convert. I haven't read the documentation to find out why exactly this works, but I found that always converting images and surfaces has a huge effect on the game's performance. So if I put in these values, if I can convert all of these images and surfaces and run the game again, we can see that now we get a very solid 60 FPS, and we're not dropping down to like 50 or 40. The final thing we're going to do to wrap up this part is to improve some of the random allocation of the trees and rocks. Right now we're placing trees and rocks based on a random number between 1 and 100, which works okay, but especially when we look at a larger world, it just feels very, very random and not very realistic. So we want to kind of reduce the randomness slightly and make it look a bit more structured. To do this, we're going to use perlin noise. The easiest implementation of perlin noise I found is using the noise package. We're going to define one parameter up here, so self.perlin scale. I'm going to make this grid length of x divided by 2. Then down in our grid to world method, where we're creating these tiles, we're going to, underneath our random value between 1 and 100, we can create a new random value, this time coming from the perlin noise, and we can say noise.pnoise2, because that's the 2-dimensional one, and we need to supply an x and a y value, and we can use the grid x divided by self.perlin scale, and the grid y also divided by the self.perlin scale. And to make computations easier, I'm going to multiply this by 100. At least it makes the values on a more similar scale to our random number. And I can say if perlin is greater than or equal to 15, or perlin less than or equal to minus 35, then we can say tile equals tree. So the idea of this is we want to kind of create clumps of trees to sort of look like woods and forests. Otherwise, let's fall into this logic, and I'm going to, because we already have trees, I'm going to reduce this to only being 1 out of 100, and similar with the rocks, just, so I'm going to make this 2. So now, running the game, we get kind of large clumps of trees and the occasional rock and tree, which I think is a slight improvement to what we had before. I mean, obviously we could continue with this and get much better and more realistic simulations, but this will do for now.